Hello, good afternoon, good morning, good evening, or good night, depending on when you're watching it. It's Friday afternoon. You can see the sun is shining back there. It's a blustery Friday, and I'm finally getting around to recording the video for you guys that are promised on validity. It's based on the slides that you have in your readings booklet that I provided you there. I've edited it a little bit to make it a little more efficient and still get the information across. I will have all the slides here. You have them in OneNote. Pop in a few notes here and there. And without further ado, here we go. So as you remember from last semester, validity, we have internal and external validity. And so we created, and you saw a video of this little checkbox way of doing an assessment of the validity of research. So we're going to go a little bit more into information bias, selection bias, confounding, and then in external validity, again, we have a selection bias appears here, and description, so description of external validity. So threats to internal and external validity, sorry about that, come from either well, that comes next slide. Right now we're just defining them. So the degree to which a measurement or study reaches a correct conclusion, that is the definition of validity. So the key word there is degree. So it's never black and white. So the vaccine research that we're hearing about now, you can see there's a lot of discussion about which vaccination is better. We have a task force group that's going to sort all that out for us. So what is the correct conclusion? It's not always clear. And so this is the next thing I want to make sure you guys think about. And so we have a lot of people, and we can see it now with this pandemic around us, that are rushing towards simple and wrong solutions. And the complex but correct solutions are sometimes a little bit harder to see, or often a little bit harder to see, take a lot more work to figure out. Types of error. So this is sources of error. Systematic error. And think about, you hear about racism, and so that term systemic racism really kind of connects to this notion of systematic error. It's built into the design and into the conduct of the researchers, when we're talking about research, or in our social spheres, in the conduct or the design of our, even our laws, even our educational system, even what we teach and how we teach it, the teachers, how they behave. So we can examine validity through the same eyes as if we want to examine racism or other flaws that we look for in the world around us. And to name it a flaw is important because it's hurtful. When we do bad research, it's hurtful. When we have a systemic or systematic error, that comes out with bad research that ends up hurting people, just like systemic racism ends up hurting people. Random error, that's something that we've been studying and looking at, the notion of randomness, through the notion of probability and the mathematics and statistical methods, and we'll touch on that right at the end of today's presentation. Okay, so internal versus external. So degree to which claims about the participants are true. This you really got to spend time memorizing and thinking about. So don't just memorize the words. Think about what they mean. Degree to which claims about the participants are true. Who are the participants? Those are people in the study. External validity, degree to which it is correct to make inferences from the participants from a sample to a wider population. Okay, so I'll add in here from a sample, that is the participants. Okay, so we've talked about that as well in the previous work. Threats. So we're going to examine some threats to internal external validity. Bias is one way of kind of looking at those threats. So bias was when things lean. So again, the metaphor, if we take racism, there's biases that are built into the system, systems within which we live. And same thing with research. We can have biases in the kind of the way the questions are asked. The way the research is set up can be biased. And there's lots of research, for example, even in things like questions of heart attacks, where it was biased towards the way men have experienced heart attacks is different than the way women experience heart attacks. And so this research was biased towards validating heart attacks in men and not women. And so therefore, emergency room physicians would not recognize heart attacks or heart disease in women. So that's a systematic error that we have that comes from research into our practice. So evaluating bias is often subjective, meaning that it has to be done with a community of researchers or peers who decide, yes, this is a biased question, this is a leading question. So it's not necessarily something that can be measured. It's something that is recognized and can be fixed through good design, later by good conduct. Once data is collected, not much that can be done. Selection bias types. So here we're going to be doing an exercise 9. Types of selection bias that I want you to think about is self-selection bias, restriction bias, non-response bias, and control selection bias. So you'll notice here control selection is kind of straightforward because it's only in case control studies. So if you have a case control study, how you select the controls is important. So some of you are going to have to go, okay, what is a case control study again? It's one where it starts with a rare disease. If a bunch of people with rare disease, then you find people who are similar but do not have the disease, and then you look for exposures in the past. So you need that control group to be selected well. Self-selection, a lot of studies are voluntary or have people not responding or dropping out of the study. So those are all kind of the same. So they lead to sometimes poor internal validity, meaning that you're not getting good measurements because you're getting non-responses, or because you're getting volunteers or you don't know what non-volunteers would think, or external validity. So yeah, each one has its own little spin, and you've got to think about them that way. Restriction bias, this is where we have inclusion and exclusion criteria, things like excluding people over 65, under pregnant women, like the vaccine trials, they excluded pregnant women. So now we can't say vaccines will be safe or not safe for pregnant women. So that would be a threat to external validity. I don't know to what extent it will be valid in these situations. Information bias. This is kind of general characteristics here. Misclassification. Okay. So misclassification and or measurement error. So this is when we're actually collecting the data. So I can misclassify you as being very satisfied when you're actually somewhat satisfied. So that would be a simple or measurement error, where I measure your weight incorrectly or ask you about your weight and get a number from you that's maybe not accurate. Okay, so a little bit more about information bias here. So it comes from what we call recall bias. Okay, so memory of exposure, if you're asking people to recall. So again, case control study. In the past, were you exposed to secondhand smoke? I don't know. So same thing, interview bias. So things like, so this dates and happiness is a really good story. It's research that was done about research. And what they found was, if I asked, well, a group of students were asked a series of questions, and question 7 was, how happy are you? Question 8 was, how many dates have you been on? And there was no correlation between happiness and dates. Then the next group of students were asked about the number of dates and happiness second, or 7th and 8th or whatever, but first about number of dates you've been on, And then there was a strong correlation between dates and happiness because there was a seed planted. People were thinking about dates and then were thinking about, gee, I haven't been on many dates in the past few months. And then we're basing their happiness score based on that. So there's a bias that's built into the order of questioning. So they can get quite sophisticated. And that's why most scientists will prefer some sort of technical measures to people's response. So far, we can't really measure happiness through some sort of electronic probe of our brains. Confounding. So in a lot of textbooks, they'll have confounding as a kind of slipped in as a type of bias. In the textbook that we're using, confounding is treated as separate. So it's chapter 11 in the textbook. The other ones are chapter 10. So visualized. So confounding can act on the exposure and on the outcome. It doesn't necessarily just go one way. So how do we do it? Well, one is to known these known unknowns. If you know the unknowns, then you can identify them and restrict them. But if this is for unknown unknowns. So I'm making light a little bit, but the idea of, we don't really know what might be confounders, so then randomization really helps with that. That can only be done in experiments, so that really helps because the two groups, the idea is that these unknown unknowns will be equally mixed in both the treatment and the control group. Matching is another thing that's used. We make them people as similar as possible, but this is really for known unknowns. In the analysis, we'll see a couple of examples and we'll do an exercise with this. Controlling for confounding, stratification, standardization, and multivariate analysis. So multivariate analysis, you're going to see this in reading research. So that's where you get something, instead of just y equals alpha plus beta x, which is your standard regression equation, you'll get beta 1 x1, beta 2 x2 plus beta 3 x3 plus error or something like that. So that's, you're looking at many different variables and the effect that they're playing on the outcome variable, right? So where x is the independent variable, y is the dependent variable. Okay, so that's what really helps, and unfortunately, the courses, the way they're set up, we don't have time to do that in the research methods or those courses. So here's an example of stratification. So we did a study on the JUMP program at George Brown and other colleges a few years back, and we compared JUMP to non-JUMP group as a whole. However, what we had, so you can see here that people in the JUMP group did double the improvement. So 12, this is the mean score, mean improvement score, right? This is mean improvement. 12 versus 6, double. Great. Now, question is, roughly double, sorry, not exactly double. Now, if we broke it up, so we had hospitality students, is it double? Same thing, improve, right? Versus 3.6, 13.9 versus 8. So we can see that well, this one was kind of weird, but we see n was only 2 here. So the negative improvement means their score got worse in the post-test from the pre-test. But the idea is that we broke it up by hospitality, business, and general arts and science students. We broke it up by division, so that's stratified the analysis. So we did this, instead of just doing the analysis for all students, we were able to break it up. So stratification, because then we see whether that stratification, division, is a confounding variable or not. So this was kind of interesting, where we also, again, we broke it up. So this is the stratification, right? Strata 1, strata 2, strata 3. All right, so that's where And that's really easy to do in SPSS. Again, we didn't have the time to do that. Especially, that's what I really like to do when there's a chance within the data that you guys collect for your research methods course. Random error. I'm getting to 15 minutes, so I want to make sure that this isn't too long. Error because of unpredictability. Machines can be slightly poorly designed machines, so reliability factor of machines. There's some error in the machines. Humans, also how they feel on this or that day. There's all kinds of randomness that comes into play, or just sampling, right? Even random sampling can produce error. Well, we know that. So it comes from measurement or from sampling. Okay, so you can read this. I'm not going to read it out to you. Here's a example of a weird sample. So you can just imagine an urn holding 50 white and 50 red balls. So it could be people. You draw a random sample of 4 to estimate the proportion of red balls. We know it's 50%. Is it possible that you draw 2 red and 2 white? Yes. But you could also draw 4 red balls. There's 50 of them, right? You're reaching your hand in, you grab 4. It is possible, not likely, that you'll get all 4. But then you're getting a weird sample. It's misrepresenting the proportion of white and red in your sample. And the answer to that is replication. If you remember back to the first week of the Stat 201 course. So we replicate. If we don't get the same result, we replicate again. And then after a few replications, we get a settling down. And so that's the notion of the, if you remember back to the distribution of sample means, or in this case, sample, sorry, not means, or sample proportions, right? So if we do a bunch of resamplings and re-studies, so that's where replication is really, really, really important, then we might get 1 weird sample, we might get 2 weird samples, but if we do 10 samples, overall we're going to be set and understand the actual true proportion. So last slide, remember this, statisticians don't say the mean is 4.3. We don't even say the mean is probably 4.3. We don't say the mean is close to 4.3. All we can manage is, I am 95% confident that the mean is between those 2 values, and we go on and on at length telling you how wrong we probably are. So that's my pitch for confidence intervals. So if you're reading research and they're not providing you with confidence intervals, you are missing good information which will help you assess the validity of the studies. And this I will leave for discussion in class. The key thing I want you to focus on is the relation between the p-value here and the confidence interval. Remember, p-value reject HO when p is less than 0.05, right? So again, this is my pitch for the confidence interval by reminding you how it works. All right, so I'll stop there. See you guys on Monday. Have a great weekend. See you guys Monday. Have a great weekend.